Thank you, Angelica. And that gets us bang on at 9:30. We're incredibly strict on the time now. So let's start with the first speaker, Professor Giuseppe Longo. He is one of the members of ENSER, and he is the chair of the French Association of Friends of the Thunberg Generation, the co-organizer of this conference. He is also a member of the scientific team that put this conference together. He was one of the people who generated the idea for this conference. He works for the French National Center for Scientific Research, CNRS, as well as for the École Nationale Supérieure, both in Paris, and for several other organizations, which I leave to him to introduce if he wishes. He's a busy man. He's basically a mathematician, but he has 4 fields of work, really. And I need to get my note out where they are. There they are. Right, he is specialized, first of all, in mathematical logic and computer science, then in cognition and the foundations of mathematical knowledge, thirdly, in theoretical biology, and finally, in the interfaces between computability, physics, and biology. I think that provides a sound basis to start this conference on. He will speak on causality and novelty production in biology. Well, at a normal conference, you say the floor is yours. With all these online conferences and meetings, I've got used to saying the screen is yours, but now, Giuseppe, I can say both the floor and the screen are yours. Giuseppe.
Thank you very much for being here. I'm very pleased both to be here and to be a member of ENSER and as well as of AGT. We strongly need to support our academic research with extra organizations, which are a place for a free debate that is more and more difficult to find, both in academia and in society, I'm afraid, in particular in time of emergency like this one. Personally, I'm a mathematician, as Diedrich said, but since 25 years, I started collaborating with physicists, first of all, and one of them is here, then with biologists for at least 12 years. Some based in Boston, other in Paris, and that's been a wonderful experience to approach these sciences from a different perspective and see the richness and the limits of them. What I'm going to talk today is a very general, theoretical, almost philosophical issue, and I'm very pleased to do so, to stay on a very general theoretical level, because every day, as many of us, I'm obsessed by the emergency which relates to discussing about COVID or CRISPR or the other various matters that concern our life in the ecosystem and in society. So for one, let's go back to the fundamentals, which are very important also to discuss the specific issue that are today's concern of everybody. Can I have my slides? Yes. Okay, I can do that now. Okay. Okay, I will basically tackle 2 issues. I will try to discuss causality as it is understood and framed in physics since many centuries now, and compare it with what we mean by causality in biology, which I think is a largely open issue. The situation is, in a sense, more difficult.
How does he get the next slide?
By the way we did it before, by pressing the button.
Down. No.
What is wrong now?
Sorry, we have a little problem with having the slide.
PowerPoint slide. Yeah. Let's stop for a second.
There we
Yeah,
are.
it works, but hold on, we have to screen share again.
Yeah.
I don't know what the problem is right now.
I'm sorry.
No, you can just do it here.
No. Doesn't work. Okay. Okay.
Yeah.
So let's start with the approach in physics, where the situation is very rich. We have several centuries of experience about discussing about causality. Of course, it goes back to the Greek inside. But in physics, the situation radically changes when some fundamental principle provided a global frame to the notions we need to talk about. It is clear that the scientific revolution begins with a method which is the ones that we refer to basically to Galileo, but there were many others before he came down, and then Descartes largely contributed to that. The key invention of Galileo was a kind of limit principle, the principle of inertia, namely the fact that there is room for rectilinear movement as a default state of matter. You see, by proposing this principle, which is very abstract, you cannot see it. If you look around, if you make experiments, Aristotle was right. Everything that you stop pushing, it does stop. Then Galileo, by proposing this limit principle, he puts himself at the horizon of all movements, made them understandable at once. Because at that point, he could start working at it could start working at what modifies this inertial movement. And moreover, it implicitly proposed something that was made explicit shortly later, namely the principle of relativity. The laws of physics are exactly those properties that do not change when moving from a reference system to another in an inertial relative movement. His example, a falling body in a boat, you could say a train for our imagination, you know that it falls together with the inertial system of the train if it is going in at a constant speed. The fact that this limit principle is posed is an abstract move that, as I said before, allows to understand movements in general, because at that point, he could study what modifies the causes that modify inertial movement, namely gravitation and frictions. Instead, he leaves his reasons for analyzing nature, physics. Einstein added a further revolution, in a sense, a strong generalization of relativity by other transformations beyond those that the successors of Galileo could analyze. Then the strength of the proposal was to identify gravitation with inertial movement. Simply, the structure of the space radically changed. The space is no longer the Euclidean in a Cartesian frame, but it is a Riemannian variety that changes the curvature space. Again, general principle modify deeply the context of causality. Why? Because at that point, in view of some other results by Noether and Weil, and this identification of inertia, which is momentum conservation property with gravitation, one can use a beautiful terminology to embed causality, namely conservation properties, in particular momentum conservation property, is a symmetry. Is a symmetry in an equation. This is a rather technical matter, but it's very beautiful, as given, as I said before, by Noether and Weil. The identification with gravitation inertia allows to say now that a body falls for symmetry reasons. You understand the beauty of this. In a sense, it goes back to the relevance of symmetries in Greek culture, in Euclidean geometry, and it embeds in an understanding of physics which is totally unified, at least from this point of view. Causality is not excluded. You can keep saying a body falls as a cause, and this is caused by gravitation, but it is beautifully understanding this general frame, which is the symmetry properties that describe energy conservation. We try to summarize this framing of causality, which for me is a key point that we raise in biology, by a short sentence in a book with the theoretical physicist Francis Bailly some years ago. Causes become interactions, and these interactions constitute the fabric of the universe. They form this fabric, and the interactions appear to be modified, intervene upon the interactions, and the fabric will be modified. Again, this is a major contribution to knowledge, as we see as a kind of monument constructed by theoretical physics in 4 centuries. There is a key issue now that will come out very important in biology. In order to do this, one has to invent the right phase space. What does it mean? To choose and fix the relevant observables and the parameters you're working on. In a sense, it is a generalization of Kant's understanding of the a priori. In order to do science, was saying Kant, but indeed is referring to Newton's physics, you first have to give yourself space and time. This notion has been generalized in the 19th century by adding relevant observables, which may be energy, then you look at time, or you look at momentum, and then you look at space. These provide the main phase spaces for at least classical and quantum physics that may be further enriched or changed. During the 19th century, others invented entropy as a pertinent observable. Suitable phase spaces for quantum physics were extended to spaces with infinite dimensions, and Hilbert spaces, and so on. For hydrodynamics, namely the science of incompressible fluids, one has other phase spaces. So the greatness of physics during 4 centuries was to invent new theories with new suitable spaces to understand the phenomena in question. Change scale, and everything changes. You go from quantum physics to hydrodynamics. They are not unified. You change space, but you say a lot. Then you go to relativity theory, yet another theoretical frame, and you have another universe. The richness is exactly in this plasticity, flexibility, in inventing suitable space for understanding, then try to unify. Very difficult. Very often it's not done. When it was done, it was fantastic. Newton unified falling apples and planets, major invention. And Boltzmann unified particle movements and thermodynamics, yet that invention. Einstein unified gravitation inertia. Unifications is the way physics goes, never by reduction. It doesn't exist. So the understanding of physics goes by this invention of new theories, then unifications were possible. I'm forgetting Maxwell, for example, another one who unified electricity and heat propagation and so on. This is really what mattered. Let's focus on one of these theories, the microphysics. You see, the invention there is that while staying within the same conservation properties, which are really the unified background for all those theories I mentioned, conservation of energy, of momentum, suddenly some people discovered that the bound electron has a discrete spectrum. And also that looking at the quantum microparticle, you may have a situation of spin up or down. And the question is, how is that possible? What causes what? Well, correctly, a major physicist of the 20th century observed that when discontinuity gets in, causality gets out. I can understand this now in the previous terms. Those symmetries, which were so beautifully framing as conservation properties, causality in physics, are continuous symmetries. So when you have a situation of discreteness, which appears in phenomena like the discrete spectrum of a bound electron, or the sudden spin up or spin down suddenly in a quantum, then what causes what? Well, my preferred interpretation for this phenomenon is that, for example, the spin up, spin down has no cause. It is just poor contingency. I largely prefer this interpretation to the one by many since Einstein in the 30s, looking for hidden variables, the hidden causes. There is a lot of work in this direction by major minds, and they don't go very far. And indeed, I must say that the vision of poor contingency perhaps is more suitable, also because thinking that everything has a cause in the Big Bang is perhaps too much. Allow contingency as a component of the dynamics of the universe. In quantum physics, of course, you do have continuous symmetries, but you go to very abstract spaces, infinite dimensional phase spaces, if needed, like with Schrödinger equation. But when you go to observation, you have this amazing phenomena of discreteness popping up. As I said before, the major step and invention due to the mind of many physicists in 4 centuries is the invention of the right space work. Descartes a priori were generalized, a beautiful idea, a practice by Newton, but philosophized beautifully by Kant, again found its application in any theory in physics. As I said before, I keep insisting every time one changes scale, changes phenomena, you may need to invent a radically different phase space. In each one, you will understand causality in a suitable way. In some cases, forgetting causality, say it is poor contingency. This phenomena has no causes, and you assume this. Again, the background frame, the methodology of fixing a phase space, of allowing conservation properties in it, is common to the different theories. And also there is something more which is common. The fact that the physical objects are generic. What this means that you can make an experiment on one falling stone, on one electron. It is worth any other stone, any other electron. If you have the right theoretical frame, if you have the right methodology in experiments, you can fully generalize your experiment. And the trajectories in the suitable phase space will be specific, will be geodetics, optimal path. Even if you throw dice, they will go along a geodetics and optimal path. Of course, you cannot predict, you cannot compute with too many variables, too many approximations in your measurement, so no way. But a dice, a river in a very regular path will go along the best path. That's really the common issue, even in a Hilbert space in quantum mechanics. That's the way things work as a consequence of conservation properties. There's another key common issue in physics that is a major problem for us in biology now. Phenomena have no history. They are state determined. Even in the case where there is a discussion of path dependence, everything is done, I cannot get into details now, to invent a suitable phase space so that you transform the situation, that you know the initial and border condition, and you can determine the trajectory in the broader sense. Determine doesn't mean predict, of course, it may be highly unpredictable, but the determination is given by an instantaneous choice of the situation. Even in the path-dependent cases, the reduction is done to the present time to look at the future. There are, of course, reversible processes, typically far from equilibrium system, a hurricane, a flame, other phenomena such as planar cells, There are all systems, like the system in cosmology, that are highly irreversible. You cannot have a hurricane go backwards, of course. Yet, any form, any shape is geodetics. You see, it's a hurricane. If you look at any surface there, any trajectory, this is an optimal path. It may be very difficult to predict where everything goes. Of course, you have many forces, many frictions. Yet, the determination is given at a certain instant. It is a state-determined system, irreversible, of course, which is the same since always. It has no history. A reversible time, yes, but not an historical time. Hurricanes, Bernard cells, whatever you want in this physics of far from equilibrium system, are identical since 4 billion years. You use the same mathematics, the same conceptual frame to analyze them. Life has been somewhat changing in the last 4 billion years. Life has an history, as I will spell out. Surfaces, forms in organisms are not optimal. They are historical, as I will insist. So let me summarize the situation in physics. There are generic objects. One is worse than the other one. The trajectories are specific in the sense they are optimal. There is no history. Conservation principles are really the leading frame. In each theory, one has to fix a phase space. Again, phase space, what it is, because that's where we start being in the route. The challenges we are facing in biology. If we choose as phase space the pertinent observables and parameters, then that's what doesn't work anymore if you look at an historical science, like evolution. Because if your observables, as they are for me, are the phenotypes and the organisms, they change during evolution. The pertinent parameters affecting these phenotypes also change. And you cannot give a priori a phase space. Indeed, some mathematicians, in particular, top one, René Thom, did realize this. He did a beautiful work on morphogenesis with physical tools, biological morphogenesis. But in the late, well, not so late, quite early, I would say, quite early understood that this was incompatible with Darwin's theory. You see, and he says that explicitly. This affects very seriously the scientific nature of Darwin's theory of evolution. He had the courage to understand the point, and as a mathematician, working with the physicist perspective, he challenges the scientificity of Darwin's theory. I believe that Darwin's theory is the science, but I do appreciate a rare mathematician or physicist working in it, acknowledging this, while most of my colleagues, I must say, in morphogenesis, just apply the tool from physics and get into biology without any critical insight. So chapeau, I would say in French, to someone who acknowledges the point. So the challenge now, the first challenge is not the only one, is that for framing causality, we miss this fundamental methodological frame which physics has so beautifully working. Give first a phase space and you look at conservation properties, what aspect they take in that. Then you will soundly discuss causality, and I hope I give you the few key examples. Okay, but let's take the methodology, at least of physics, of first spelling out the theory. This is something we learn from the Greek, in particular in mathematics. Spell out your principles, your axioms, your fundamental concept, and that's science. I'm stressing this because now we are very often facing with technoscience, which is a common tool to intervene even when inventing vaccines. Just use a technology with no principle, and then we are in a mess. That's very common, in particular in molecular biology, that is a technoscience, it's a collection of technologies, and there's no general principle or wrong general principles like the central dogma and the exact stereospecificity of molecules. This is just to say that it is possible to apply technology, provided you spell out the principles and you discuss about the principles, and they are clear, strong, explicit, not vague references to information programming whatsoever. A short interrupt about the present. So let's go to science, and that's Darwin's approach. Darwin spells out two fundamental principles. The first one is 4 out of 6 chapters of The Origin of the Species, as not enough quoted, I think, is reproduction with variation. Heredity is descent with modification. And I would add motility, as my colleague, Carlos Sonesana did very soundly, thinking also of the cells in the node. The second principle of Darwin is very well known, selection, that I interpret as exclusion of the incompatible. Look, the radical change of this great theoretical and scientific mind. These principles are incompatible with physical principles. They are non-conservation principles in a sense. The phenotype changes every time there is a reproduction. In discussions with my colleague, we prefer to add more principles, and that's where I intend to frame causality now. Both philo and ontogenesis are an iteration of a morphogenetic process, which is never identical. That's the key point. Reproduction, even one cell reproduction, produces 2 slightly different cells. This is a key to differentiation. This is the key to production of diversity, variability, thus stability of life. Life has this suitable stability that is due to population, to an organism, to a species, and the never identical iteration of any morphogenetic process is at the core of the stability. If you have a population in a valley of a few thousand individuals, this is more stable. If it is diverse, if thus there has been this variation in reproduction, which is a core property of biology. And then there is another principle that I will like to hint to, but I hope Mael will do more, that the organization, in particular in organism, multicellular organism, but quite fully general, must be understood in terms of a closure of constraints. I will try to hint more later. I claim that these are the least condition of possibility for constructing biological knowledge and then understanding causality within it. Of course, with that, you have to invent a space, but the challenge that it will not be a constant one, it is part of the dynamics. A phylogenetic trajectory constructs its own phase space while advancing in historical time. That is the challenge we have, historicity. For me, historicity is exactly characterized by these 2 major phenomena, in evolution at least. We can discuss about what happens in ontogenesis, but that's a very delicate issue. So if we choose as a phase space the one that we observe, phenotypes and organisms, and their pertinent parameters, this keeps changing. Metabolism typically changes radically during evolution, from early bacteria to the ones that had oxygen, that created oxygen 2 billion years ago, and so on and so forth. Eukaryote cells. And then there is also something very peculiar, the role of rare events. I don't know, let me just mention the formation of the mammalian placenta. Many of you know that this was a retroviral infection that happened several times between 100 and 40 million years ago. This infection, I guess, killed many of these poor females who were roughly as mammalian marsupial. But then something happened. The rare, incredible fact of passing in the germinal sequence, germinal cells, and then becoming hereditary, and the restructuring of the vertebrate itself, becoming a placenta. As a consequence, a retroviral infection. By the way, about 40% of our DNA seems to be due to transfers, mostly due to viral transfer, retroviral transfer. So what is this? Surely there is a cascade of rare event that allows such a change. Look, that when I'm saying that rare events happen all the time, what do I mean? Is that the type of being rare is very frequent, but each of these events is very rare. There is work in physics about rare events, for example, the book on large fluctuations and the work on large fluctuations that are rare, but physicists acknowledge that it is rare that the trajectory is affected by a rare event. What I'm saying now, that if you look at any phylogenetic trajectory, it is marked by many rare events, each of them very rare. That's really the historicity, the crucial historicity of biology. And let me say, of any historical science. So that's why we are proposing, some of us are proposing a mathematical difference. We have to treat thermodynamic irreversible time, like the time of hurricanes or flames, with a given parameter, and historical time with another one, or at least there must be two different observables. We have an ongoing debate with some colleagues in mathematics where they should be treated on the same line, on the same parameter, or with different observables of two different parameters. But we need to distinguish these two forms of time. One is the reversible time of the thermodynamic processes that, of course, are omnipresent in life. There is transformation of energy in any cell, of course, but also there is the historical time that I am characterizing by the changing phase space, the observable change, novelty pops out, and the role of rare events. So this history goes along by the construction of new phase space. Of course, this construction is heavily canalized. It cannot be anything. The traces of the past, most of all, a major physical chemical trace of the past, which is the DNA, which is an internal constraint to every cell, something absolutely amazing. In every cell, there is an internal constraint, which is a trace of an entire history. That's, of course, totally crucial in canalizing the future. Okay, let me give you a couple of examples of creation of new novelty. It is now rather well established that the eukaryote cells are the result of a symbiosis. Two bacteria prokaryotes joined and provided within another prokaryote mitochondria and chloroplast. You see, in a case like this, DNA follows. It is not the protagonist of this radical change, the invention of eukaryote cells. But some claim that also the nucleus of eukaryote cell is an invention due to a symbiosis. This is an analysis based on the peculiarities of polymerases in some algae that seems to be really predecessor of what happens in eukaryote cells. I think this is still an open issue and analysis, while the first one seems to be very solid. A typical example of radical changes of the observables, because metabolism changes, production of energy, mitochondria get a new role when installed inside the cell. And the phenotype eukaryote cell is a true revolution. The phase space, the pertinent parameters that you have to look for changes. Of course, the constraint of DNA is there. The constraints matter a lot. Look, for example, how the constraint of history forces homology, by homology, the very strange shape of a batswing. There's no way to analyze the wing of one of the other, but in historical way, birds' wings are homologous with our arms and those of the bats with our hands, or recognizes the traces. Because of this, they are not optimal. They are not optimal in the shape because the trace of history constrains the dynamics. But look also at our hand. It's not optimal for grasping a branch. Well, it works for grasping a branch, but exactly because it is not optimal, you can flatten it and use it to flatten corn or to caress another mammal, which is very convenient. This form of exaptation, and in a case like the hand of overloading, you overload the hand with new properties and qualities that were not there before. You can also play piano with the hand. This overloading is typical of a changing of the pertinent observable relative, and it is possible because there is no optimality. If our lungs were optimal, as some physicists who compute and did compute quite soundly the fractal dimension, our lungs have a fractal dimension which optimizes the flow of energy and matter through a surface in a volume, so you can compute it to be 2.3. But if you look closely to the lungs, well, they are very regular. They have different fractal numbers according to this area. This is fundamental to be adaptive. You breathe different in different contexts, atmospheric pressure, humidity, and whatsoever. Some parts of your lung will work better than others. That's fine. If we had an optimal physical genetics as the fractal number forecasted by some physicists, we would be dead. Okay, so this production of diversity and this adaptivity goes together with not falling genetics in organisms, in phylogenetic part, in the phylogenetic part of any organ in an organism. So let me go back to this key point. We reverse now the situation with respect to physics. Evolutionary trajectories are generic. They are possible ones. They're not uniquely determined, like the geodetics in physics. As I said before, these peculiar paths are not optimal. They are not uniquely determined. They are historical result of changing constraints, internal constraints, external ecosystemic constraints. And any organism, bat, bird, whatever, is specific, is individual, is historical. And as I said before, the crucial challenge is that we have to work in a theory where the phase space itself changes. I insist, this is because Darwin started theoretizing our most robust theoretical frame in biology, Darwin's theory of evolution, by proposing non-conservation principle. Fortunately, he didn't know Hamilton, who was his contemporary, who made the revolution in physics by the variational method applied to conservation principles, but they were doing very independent work. So you see, that's the situation I gave before in physics. Let's see what happens in biology. Generic objects become specific objects, historical, specific trajectories, optimal, are generic, possible ones. There is no history in physics. Everything is history in biology. Phylogenetic, ontogenetic history is crucial. Conservation principle, non-conservation principle, principle of variation. Fixed phase space, changing phase space. That's where we are trying to embed causality. Mathematics, well, so far I think there is none, but there are some colleagues and friends of mine and of us, Sarti, Giovanna in Paris, Giovanna Citi in Bologna, and others who are working a beautiful mathematical frame, heterogenesis, with taking care of historicity. They came from reflections from philosophy. We knew each other since long. They are now taking care also of our concerns, the ones I mentioned now. I think the heterogenesis is a revolutionary approach to historicity by mathematical tools, where the dynamics construct its own phase space. It's non-obvious mathematics is being done. I won't say anything about that, but to say that fortunately also mathematics has an history, is a matter of invention, so we don't need to be in the fixed frame as René Thom told. Let me summarize that. In physics, causality is beautifully understood within conservation principles, beginning with energy conservation, momentum conservation, so that we get to this top understanding of provided by relativity that you can understand in terms of symmetries lots of phenomena. And you know, this is a general way physicists understand and propose and theorize. So they discover particles because they say there must be something there for symmetry reasons. And that's beautiful. In biology, we want to replace them by an ongoing construction of a theoretical frame where our principles that I tried to spell out are based on the genericity of trajectories, historical specificity, non-conservation. Let me also repeat the same principle in a slightly different language, maybe more familiar to you. It's the language of agency. The principle that any organism is first of all active, it reproduces with variation and moves under constraints. That's a key property even of cells in an organism. A priori, they reproduce with variation and move, but they are constrained by the tissue, by the hormone system, by all what connects to each other very firmly with different extremes. We have practically no reproduction in the heart cells, a lot of reproduction in the intestine, of course, in the epithelium of the intestine. So the differentiation is due to the very different constraints these cells are in. But the limit principle, comparable to limit principle of inertia, which you never see, there is no inertial movement around us, but is the general principle that started modern physics. Like in that case, the limit principle is reproduction with variation and movement. Then enablement, making possible. Under the principle of an agency as an a priori, it is the context that enables. So you may well say that the microorganism causes by agency a disease. A given bacterium is causing you pneumonia. It's very important to understand. But the good doctor has to understand what enables it. If you have an immunodeficiency, if you were too stressed or whatever, the enabling condition makes many of the microorganisms that typically cause disease suddenly become dangerous, while they may have been for years or forever in your body, but the enablement was not there for them to become dangerous. You have to move away then from a frame that still now is governing most of biology. At least I've seen that practically all books, all school books in medicine and biology still refer to the central dogma in various forms, that causality bottom up. That is really not only a wrong principle, but it's framed in a language that makes it not falsifiable information language, because it being totally unsuitable. It doesn't even allow a sound discussion, and it is still there. What's amazing is that very often biologists, molecular biologists, the mainstream ones, there are some fantastic dissidents, the mainstream molecular biologists, when in private say, oh, I know it is not true, but you know, it's very simple and so on. There is this double language for lack of other principles. So they still are there, and experiments, invention of GMOs, they're putting them on the market and so on, all depend on this vision, which is still there. We are slowly moving to other frames that, in a sense, make more specific Nobel's idea of biological relativity. That's the work on constraints by many, in particular by Monteville and Mossio, that is a way to organize biological relativity, the way the different level of organizations in the arc and have no causal priority is quite crucial. Let me now do something quite daring. Namely, I would like to face a situation where we deal with molecules. I think all levels are pertinent of analysis, and we focus on organisms, and the principles I spelled out concern organisms and phenotypes. But let's try to turn this collection of technologies, which is our today molecular biology, based, as I say, on principles that the workers in this discipline, in private, say that they are not valid, but they refer to them constantly. And indeed, since the work by Jean-Jacques Cupiec in '83, we have to change radically the perspective of how macromolecules interact in an organism. Macromolecular interactions are stochastic. They must be given in probabilities, and these probabilities depend on the context. That's the principles to be used. Fundamental work has been done 20 years after Jean-Jacques Cupiec in Lovitz and others, much more documented, of course, much more empirical evidence, and there is a strong minority of molecular biologists that fortunately are referring to this as a key principle. Then more provocative remarks that I hope can be really turned into principles for a new insight. Almost all, most common phenotypes use almost all DNA. Almost all DNA is used, expressed in almost all cells in an organism. It's a matter of different probabilities. You see, this goes radically against the current frames where one thinks that by putting a fragment of RNA, there is an exact production of a molecule, a fragment, an epitope of the spike molecules that will adhere like a key in a lock. This is not how things work. Finally, the cell and the organism and the ecosystem strongly canalized, enabled by constraining macromolecular interactions, starting with the gene expression. So it is not the molecular networks that completely determine the cell, the phenotype, the organism, but their very existence, the molecular interactions, the molecular networks in a cell are made possible by constraints, by membranes, the cell structure, the hormone cascade, the organism, the ecosystem. Again, one cannot understand the organism in terms of molecular networks because those molecular networks exist, are made possible only within a cell, within an organism, within an ecosystem. By the way, most of this molecular structure, the macromolecules and their networks, exist only in a cell, as they are the result of a history and nothing else. They are physically, chemically almost impossible outside a cell. They simply don't exist. Of course, as I was saying now, the consequences are very strong, and this we insist in a volume which is a collection of papers with Anna Soto and Dennis Noble. It is the cell in an organism ecosystem which enables the macromolecular networks. They, of course, produce the organismal constraints in a cell and organism and ecosystem. That's what is summarized by the new insight into causality given by the closure constraints. Causality is the result of a network of interaction. No causal level is privileged, but these interactions are organized as constraints to flows that generate those constraints, also indirectly. Let me conclude with a complicated diagram in a very interesting paper by some colleagues and friends, where they analyzed the glycemia regulation network, which is not a network. It's a system of constraints at 3 different levels as they analyzed it, where causality goes up and down and relates both specific structures like, I don't know, liver cells and flows. So the control goes to structures, to flows, and flows that control structure. I will not get into the detail, but I strongly recommend the paper as a very beautiful exemplification of this view of the historical formation of multi-level constraints as the framing of a causal structure. I conclude now here, giving here some reference for books that I like very much. They are accessible to everybody, I think, in principle, and the paper, and then some work where I contributed directly as conclusion. Okay, thank you very much.